So we continue our carboxylic acid derivative odyssey by diving into some interesting new acronyms. And I've got this first mini lecture entitled Acronym Soup, focusing on the Hell-Volhard-Zelinsky reaction, but that's not the focus at all. We're pretty much going to gloss over all of sections 1 through 6 in this mini lecture. Okay, so the introductory material in Chapter 21 is really review material from Chapter 20. We call it alcoholysis, hydrolysis, aminolysis. You know, it's all the same. Don't get befuddled by the names. It's all lysis. Lysis meaning we're cleaving that carbon X bond, where X, of course, is our leaving group. And the mechanism, all the same, just like we learned last chapter. Attack of the nucleophile at the electrophilic carbon. That makes the tetrahedral intermediate. And to regenerate our carbon-oxygen double bond, we don't do that. That's certainly possible, and in fact that's why this is a reversible step. But what we want to see happen is X get kicked out to give you your substitution product. So nucleophilic addition here, elimination here. So that's where we come up with our addition-elimination reaction. There's the product. X minus kicked out. It doesn't matter if you want to call it alcoholysis, hydrolysis, or aminolysis. The nucleophile does the same thing. And also note that the nucleophile can be neutral. The mechanism doesn't change significantly at all. This guy is still the electrophile, and your nucleophile is just uncharged. We have a couple other proton transfer steps involved. So, what else is introductory or review material in Chapter 21? Well, this whole rates of reaction stuff, which is sections 21.2 and 21.3, is really just re-emphasizing what we already learned about the reactivity ladder in Chapter 20. So, as we saw in the energy diagrams in Chapter 20, that first step is a doozy. Making the tetrahedral intermediate is pretty much all uphill because you're breaking that nice strong carbon-oxygen double bond to make the tetrahedral intermediate. So that's definitely our rate determining step. But just how high that energy hill is defines the reactivity of the carboxylic acid derivatives. So it's really all focusing on X, that leaving group, and how it impacts the electrophilicity of the carboxyl carbon. So, one thing that's reviewing, taking us way back to even Chapter 1 of 2301, is the impact of inductive effects and electronegativity. So, oxygen versus nitrogen, what's the difference? Well, of course, it's all electronegativity. And so when it comes right down to it, this versus this, a nitrogen being less electronegative is a lot more likely to donate, well, let me just say, it has a much larger contribution of this resonance contributor than does the oxygen. Okay? Because nitrogen is not as electronegative. So an ester or an acid, well, you know, it has the same resonance contributor too, but this one not as favorable because you're putting a positive charge on an electronegative atom. So that's kind of Chapter 1 stuff. Geez, charge is stuff from 2301 as well. A carboxylate is a lot less reactive than a carboxylic acid, Why? Well, my gosh, if you got a negative charge on that, why would a nucleophile want to attack? And then really, it kind of boils down to a size argument when you're looking at acid chlorides versus amides or esters, because you have a much larger atom in terms of the chlorine. That overlap that we like to show with resonance delocalization, it really doesn't overlap as well. The orbitals just don't match up well. So inductive effects, electronegativity, charge, size, this is all stuff that we have used over and over again in OChem to understand acid-base chemistry, nucleophilicity, electrophilicity. So we're just doing it all over again. This figure out of Carty on page 1012 sums it all up. So what I particularly want to emphasize is the fact that the tetrahedral intermediate for all of these starting materials, this is for the reaction of any of these with the nucleophile water, but it really doesn't matter what the nucleophile is. Note that the tetrahedral intermediate is pretty much the same energy level no matter what the starting material is. However, look at the starting materials. There's a huge difference in their reactivity. There's a huge difference in their stability. And that's based on what we just covered in the previous slide. So, what it boils down to is we can tie this all together and see why the reaction of a carboxylate anion with a nucleophile is so incredibly slow as opposed to, say, the reaction of the acid anhydride with the same nucleophile. The acid anhydride's energy level is so much higher, it makes the delta G double dagger a lot smaller, and thus the reaction a lot quicker. So these all pull everything together to kind of give you a better understanding of why the reactivity ladder is the way it is. And it's basically all leading up to this. How do you get to the top of the reactivity ladder? Because otherwise we're not going to be able to convert any of those less reactive carboxylic acid derivatives to something good. So the way you get to the top of the reactivity ladder is you prepare acid chlorides. So this is really all about going from an acid, which is low reactivity, to the acid chloride, which of course is at the very top of the reactivity ladder. And we can do that using these two reagents, thionyl chloride or phosphorus trichloride. What? More review? Well, certainly the phosphorus trichloride is more review because we saw phosphorus trichloride, phosphorus tribromide in going from an alcohol to the halide, PBr3 or PCl3, took you straight to the acid chloride or the acid halide. But what about this thionyl chloride stuff? Well, look at these reagents for a second. First off, with the thionyl chloride, boom! You've got a sulfur-oxygen double bond, which we know, Nancy always is saying, think about that X oxygen double bond. No matter what it is, no matter what X is, it's going to be a great electrophile because of that resonance contributor. Okay, another thing we can look at here is boom, 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 boom. We have seriously polar bonds from the chlorines attached to the sulfur, the chlorines attached to the phosphorus. So that too is going to make the sulfur and in this case the phosphorus, very electrophilic. So even though both the phosphorus and the sulfur bear a lone pair, they are both electrophiles, big-time electrophiles. And what's your nucleophile? Well, that kind of goes without saying. It's that nucleophile. It just happens to be tied up in the carboxylic acid. So, there you go. I take thionyl chloride, I react it with my carboxylic acid, and voila. I replace my OH group with a chloride. Or do I? What's wrong with this picture? You know, we don't talk a whole heck of a lot about conditions, but if Frida Chemist goes up to the lab and tries to run this reaction in an aqueous solvent, Frida is going to have some serious issues. And Frida is probably going to end up in the hospital because thionyl chloride reacts really quite violently with water. So always remember, HOH is definitely going to compete with that OH. So you can't run these reactions in the presence of a competing nucleophile. Alright, this looks better. All you have to do is throw in your carboxylic acid with maybe a slight excess of thionyl chloride, and there's your acid chloride. I should probably mention that thionyl chloride is really an evil reagent. It is the best reagent to use, but it is terribly reactive. It smells a little bit, incredibly corrosive, and if I'm not mistaken, I think it might have been used in chemical warfare. Other than that, it's a great reagent. Okay, now I'm doing a little skipperoo here, and I'm throwing in this next example from 2 sections ahead, section 21.6, because I want you to see how similar all this stuff is. So here I have an electrophile that's going to react with my sulfur oxygen double bond. I'll get my tetrahedral intermediate, and then that'll come back out, kick out my chloride, and ultimately I end up with this guy, and the Cl minus that was kicked out can go up, down, out. Woohoo! And what you end up with is you lose SO2 gas and you get your acid chloride. Okay, pretty cool. Same thing does in the next example, right? So it's not a carboxylic acid, but still an OH. And I'd expect to see the old, we'll just do this guy. So we got the same thing here. Alright, and then that's positively charged, and then kick that down, kick that out, and up. Here we go. There's our product. So I'm leaving the mechanistic details to you and the textbook, but what I want you to see is that there are some clear similarities and some important differences between the example on the top, where you want to make the acid chloride, and the example on the bottom, where you are stopping at this sulfonate ester stage. So the similarities and differences. In both cases, our nucleophile just does the initial addition. And in both cases, the sulfur-oxygen double bond is regenerated with the elimination of the chloride anion. But then, for thionyl-chloride, the reaction proceeds because you're kicking out Cl-, well, you did with the other one too, but that Cl-, should use this guy, can kick out, help, and make lose? Boy, that's terrible. It can kick out a fantastic leaving group, better than anything you can possibly imagine. Any gas is a fantastic leaving group. And so the reaction continues. So you've got two chlorides in this reaction and a super good leaving group. In the bottom example, one, you only kick out one chloride. It gets trapped by the pyridine that's present in the reaction. And the bottom line for this particular example is that you stop at the sulfonate ester. So I wanted to really drive home those differences because you're probably going to ask about that at some point.